Okay, are we live now? And people over Zoom can hear me, right?
Yes.
Okay, perfect. So then, let's get started. Hello, everyone. Welcome to another lecture in computer architecture course. I'm Mohammed. Sorry for our delay. We had some infrastructure issues. I mean, sometimes it happens. But I think now we are good to start. So very brief introduction of myself. I'm Mohammed, as I said, I'm a senior researcher and lecturer in Safari Research Group. Before joining Safari Research Group, I was a postdoc in IPM in Iran. I did my PhD in Sharif University of Technology from 2014 to 2019. And if you want to contact me, you can use my ETH email with Safari ETC or my Gmail, which I can provide you if you need it. So my research areas, I'm mostly working on, computer architecture in general. But yeah, my focus nowadays is on memory and storage systems, near data processing, heterogeneous system architecture. Also, I'm quite interested in bioinformatics and interconnection network. So today we're gonna discuss about flash memories and solid state drives. We're gonna have at least 2 lectures on this topic. The focus of today's lecture is more or less on flash memory and the fact that flash memory chips are quite error prone, and how we can understand the source of errors to design intelligent techniques, basically to resolve errors and fix the issues. But for the next lecture, which is going to be hopefully on next Thursday, we will go more into SSD design, kind of architectural information on how SSD works, and some architectural techniques that basically we and other researchers develop to improve performance. So before diving into NAND flash issues, I'd like to give a very quick background on NAND flash memory operation. So in NAND flash chip, basically we have several blocks, and in each block we have several pages. So the number of pages per block can basically differ, and the number of blocks inside the flash can also differ. So I should also say that, this kind of organization of flash memory that I'm showing here is a very, kind of pictorial. In reality, a flash memory organization may not look exactly like this, but this is give you some overview of basically this organization. So each page we can have different sizes for flash chip pages. Nowadays, those flash chips that they are customized for performance, for lower latency, they usually use low size pages, like 2 kilobyte or 4 kilobyte of data. But most of the SSDs nowadays that they are optimized for density, and also they are cost optimized, let's say, SSDs, they usually use larger pages, like 16 kilobyte. So when you want to read data from a flash, we're gonna see more detail about the read operation. But basically, what you need to do is you need to apply a voltage, which we call it the reference voltage, to the page that you want to read. And for other pages, you need to apply pass voltage, which is this is the voltage which is high enough to make sure that all other flash cells are acting as a resistors. We're gonna see more detail later on soon. So this is a flash cell array. You can see that we have several kind of transistors that they are basically serially connected. So each this connection, we call it NAND string. And we have also the word line that flash cells are also connected in a row. It's very similar to also DRAM array that we have basically row and column. But the main difference here is that in DRAM, we have these capacitors, which we store the charge in capacitors, and then the capacitor is connected to the bit line with a transistor. But here, actually, transistors, that they are flash cells, are connected to the bit line directly. So as I said, this is a row, and we have also a column. I mean, to give you some analogy with a DRAM array. But yeah, essentially what makes this flash cell, I mean, the difference between, the main difference about this transistor, which I mentioned, is that in flash cell, we have a floating gate between gate and the substrate. That essentially the floating gate, what we can do is we can trap charges, we can trap electrons. And when you trap electrons in floating gate, you basically apply negative charge into the flash, into your transistor. That means that when you want to switch on your transistor, you need higher voltage. So how many of you have heard about, I mean, aware of transistors, how they work? Okay. So in transistors are very, I mean, like a switch. So, I mean, very brief overview. We have gate, source and drain. And if you apply, when you apply voltage between gate and source, like the V gate source, when the voltage is higher than threshold voltage, the transistor will be on. And otherwise it's off. So essentially what we can do with this floating gate is that we can increase the charging, negative charge inside the flash cell, such that we have increase in threshold voltage. And when you want to switch on your transistor, which is your flash cell, you need to apply higher gate source voltage. So when your flash cell is completely erased, which means that you don't have electron in your floating gate, you can consider that, for example, threshold voltage is 2.5 volt. But when you actually program it and increase it, it can be, I mean, go up. For example, we can consider as 3.5 volts or something else also. But yeah, that's the way, basically, depending on what's the threshold level is, you can encode the state to 0 and 1, right? So usually people encode basically the low threshold voltage, which is, I mean, here we consider as 2 volts as 1. So when you apply a reference voltage to your flash cell, and that reference voltage is something between the nominal threshold voltage and the maximum, I mean, the program threshold voltage. So with that reference voltage, which is something, as I said, in the between, you will see that if the transistor, which is your flash cell, is on and will basically drain the current, you will encode this as 1. But if it is the threshold voltage is high, and that reference voltage cannot switch on your transistor, basically your flash cell does not drain current, and you can encode it as 0. Is that clear? Okay. So, but the thing is that other flash cells that we have, as I showed in that picture, you know, there were several flash cells that they connected to the NAND string, like the bit line. So you need to make sure that other flash cells are, I mean, they call it inhibited. Basically, they don't interfere to your, basically to the flash cell that you want to read. So in order to make sure that they don't interfere, we apply Vpass, which is high enough to basically turn on your flash cell, no matter if it is programmed or not. So basically here, for example, Vpass is 5 volt, which is higher than nominal threshold voltage and also the program threshold voltage. And basically your transistor, your flash cell will be on, and then it will flow current. So here is the array that you can see better. Imagine that we want to basically read page 2. We apply Vpass to page 1, 3, and 4, and V reference to page 2, right? So as a result, the first, in page 2, the first 2 cells, since the threshold voltage is high, your reference voltage cannot switch them on, and basically you don't flow current in those beta string, in NAND string. And so you will consider it as encoded as 0. And for those cells that you basically, your reference voltage switch them on, basically you will flow current and you encode it as 1, sorry. I mean, as kind of a side information, we have also, you may heard about NOR flash memory. So we have NAND and NOR flash memory. I mean, today technology, mostly we use NAND flash memory because the main reason is that it has better density. But with NOR flash memory, you have basically, I don't want to go into details of how people make NOR, but the thing is that for NOR flash memory, you have a shorter connection or faster connection to the bit line. So for NAND string, you can see that, you know, a very large NAND string, those transistors are connected kind of serially. So you need to basically float current to this NAND string in order to understand the voltage or the status of your cell. But in NOR flash, you have more, let's say, parallel access, like NOR cell. And because of that, you have much better latency. But as I said, due to extra connections and extra wires and all this stuff, today technology, we don't really use NOR as far as I know. So, but if you're interested, I mean, you can look for that also later. So the threshold voltage, as I said, you can basically encode these two states. But the thing is that when you program your cell, we have this kind of probability density function for the normalized for the threshold voltage. So we have this distribution. So ideally, we want to have all cells that they are erased. They have exactly the same threshold voltage, and all the cells that we program them, we also want them to have exactly the same threshold. But the thing is that in reality, that doesn't happen, and we have kind of distribution that you can see here. And we will see that the one of the reasons that we have errors in NAND flash is kind of distribution that we have. So as I said, when you want to read, you need to apply voltage, reference voltage, which is something between these two. So the thing is that when you have a low gap between these two distribution, you need to be really accurate in your reference voltage. And as much as basically you you make these two margins closer, basically you're more likely to have error. So, and that's the reason that, for example, we have higher errors in MLC, multi-level cell flash chips. So you can actually divide your distribution of this graph voltage threshold into two states, and then you can encode it as 1 and 0. But at the same time, we can also divide it to 4 states. And then you can have MLC flash cells that you can basically store 2 bits inside each flash cell. But as a result of that, you have lower gap. And again, you have probably you're more vulnerable to errors. So today's technology, we usually actually use TLC and QLC, which you store, for example, 4 bits per cell. So you need to, in QLC, you need to basically divide this window to 16 states. But for those flash chips that you want to, basically they are optimized for performance, we usually use SLC because SLC flashes are faster and they have better endurance as well. So we will see also again later. So I like to show here that basically when we erase the basic state of your flash cells is erased. And when you erase it, you are in state of 1-1. I mean, you really can basically encode these states as the way that you want. I mean, for each flash chip, you should have a contract with the flash controller. But the moment that you have that contract, basically you can encode the way that you want. So here, for example, the distribution that we have, encoding that we are using, you can see that between each neighboring phases, we have only 1 bit change, right? So that's quite important in order to reduce the number of errors, because so we will see that it's going to happen that these actually distribution, they shifted they shift over the time. And so you may actually read something that it was previously in P3 state, but now you're reading as P2 state. So you have error, right? But since your encoding has only one difference, you will have only probably less errors, let's say. And more likely you can fix it with ECC. So I want to mention this because encoding is up to the designer, but there are also some reasons that why we are using such encoding. And there are also some other performance reasons that I don't want to go into detail right now, but we can discuss it later if we have time. Okay, so the thing is that, as I said, threshold voltage reduces over time. I'm not showing the erased state anymore because ideally we don't have electrons in erased state. But in other state like P1, P2, and P3, we have some electrons. Depending on the state. For P3, we have the highest number of electrons in the charge in the floating gate. So after some time, you will have some retention loss. Some of these electrons will go to the substrate, and basically you lost basically a part of your charge. And as a result of that, the threshold voltage will basically reduce after some time. So when your flash chip is working, after some time, you will see that basically these distribution, they are shifted and they are also widening. So it's not only, they are not kind of, nicely just shift to the lower threshold voltage. That's also challenging, but if they were only shifted and they don't, conflict, still you can fix your errors. You can just understand that which reference voltage I need to use. And basically, probably you don't have much errors. But in reality, they are also, widening. They are widening, and at some point they will basically cross each other, and you will basically have some port section that basically you will have errors. So we call this as raw bit errors. So ideally, in such cases, you want to have a minimal bit error. So probably you need to understand which reference voltage will reduce the amount of errors. So we will see how we can predict that voltage later on also. So when you want to program a 2-bit MLC NAND flash memory, especially in the past, we had this 2-step programming. First, we are in erase mode. But then we first basically program the LSB bit. So we have this temporary position that you program the LSB bit. And then after that, you program the MSB bit. So you go from, if you are basically, you go from this ER to P1, you cannot go from temporary position to P1. It's kind of impossible to reduce the threshold voltage. If you want to reduce the threshold voltage, you need to erase your flash cell. That's one of the reasons that reprogramming in flash cells are quite challenging, and mostly you need to erase them first completely and then program them again. So you can increase the threshold voltage, as you can see. From temp you can go to P2 and P3, and from ER you can go to P1, but not the other way around. Okay. So there is a paper that discusses about how we can architect MLC, because so each word line in SLC is a page, right? But now that we have MLC and we can have 2 bits per cell, so you can have basically different design and how you want to place your pages inside the memory. So this is, for example, one architecture that I'm not going into detail. You can check the paper if you're interested. But basically, you have these, those red rectangles. They are LSB even page sets. So you have these even page sets and odd page sets. And for each of them, you have LSB and MSB. So basically, you can distribute your data as an example in this figure, right? For example, these are LSB odd page sets. These are MSB even page sets and MSB odd page sets. But this is not something that's written on the stone. You can also have different structure if you find a good reason for that. So another thing, very brief background is that about planar and versus 3D NAND flash memory. So technology in the past was planar NAND flash memory, which kind of 2D architecture. So in order to provide enough scalability, industry have to reduce the cell size in flash memory. So as a result, when you reduce the cell size, you can trap charges less. So and you have basically you will have less margins in your voltage threshold distribution, and likely you have more errors, right? So because of that, with 2D NAND flash memory that we will see also in the rest of this lecture, that basically they are quite error prone, and they will have a lot of errors. But that's something that they have to do it because we need higher density. So at some point, the industry also moves to 3D NAND flash memory, which basically you can provide higher capacity by adding layers. And because of that, they are relieved of using very small cells, and they are actually using larger cells when they are using 3D NAND flash memory. So they can basically reduce the number of errors with that. But this is also kind of scalability issue. At some point, in order to provide higher density or higher capacity, they need also in the 3D NAND flash memory to go into less sizes, to use smaller flash cells. And as a result of that, you will have more errors. And as I said, in this lecture, we will mostly see MLC, but nowadays people are using QLC. And with QLC, for sure, you will have, a lot of errors, especially also in 3D NAND flash memory. So yeah, we will see that basically a lot of interesting research that our group have been done on this basically reliability analysis of 2D NAND flash memory. We also did some analysis on 3D NAND flash memory. I will try to cover them today, but if I couldn't, we will have them also in the beginning of next week. So the 3D architecture is something like that. Basically, this is the bit line that we also have in other. Let me find another picture. This one is easier. Yeah. So basically, they call this usually in 3D NAND flash cell. They call it charge trap. We can also have floating gate. That's a technology decision. You can also basically integrate floating gate in 3D NAND flash memory, but usually it's not easy to do that. And because of that, people, industry came up with this charge trap. It has a slightly different architecture, but essentially basically the function of charge trap is very similar to floating gate. So you have this charge trap and control gate, gate oxide, and tunnel oxide, which is, they are because of this 3D architecture. But the thing is that your flash organization are like this. So you have this board line again, and your bit line is actually connected through the layers. So yeah, that's the main difference here. So your block actually, so each block consists in one layer because of these board lines. Each block is actually in one layer, and the other blocks are connected to that also, as in different layers. We will also cover more background of 3D NAND flash memory when we want to discuss reliability issue of that, but we'll see. So if you are interested to learn more background and state of the art, I would suggest that you check. I think we will also assign this paper as one of the review, but this one is error characterization, mitigation, and recovery in flash memory-based solid-state drives. This is actually one of the best informative papers for me, at least, because it actually summarize many reliability issues of NAND flash memories. What are the challenges? What are the techniques to resolve them? And so I would strongly encourage everyone to check this paper. This is also a more recent version of that in 2018, but yeah, it's one of the chapter of this Inside Solid State Drive book. Okay, so now let's dive into flash memory reliability and security. So basically, this is a fundamental limitation of charge memory. So you already know about for DRAM that we have this capacitor charge and we have this transistor leakage. And for flash memory, we also have this floating gate, and that floating gate can leak charge after some time. So basically, that makes a lot of issue like the retention error, and we will see more. So the problem that we want to focus now is that MLC NAND flash memory reliability endurance is a key challenge for satisfying future storage systems requirement. What is endurance? Does any of you have an idea? Exactly. I mean, the number of write that you can write, program, and erase, basically. Endurance is basically for flash chips. I mean, for other also emerging memory technology that I guess Hayu was, she was discussing yesterday. We have this limited number of program and arrays. So we call this endurance. That essentially endurance affects the lifetime of your memory system. So our goal is to build reliable error models for NAND flash memory by experimental characterization and develop efficient techniques to improve reliability and endurance. And this lecture is going to provide a flash summary of our recent results published in the past 8 years in different several conferences. So I will start with kind of background and motivation and approach. So this is an evolution of NAND flash memory. That basically, in the beginning, we have only SLC architecture, and we had like 64 megabytes. And then after some time, basically, SLC flash memory get more dense, and basically the industry could increase density. And they also use MLC. As I said, nowadays we have also TLC and QLC NAND flash memory. But the thing is that flash memory is widening its range of applications. And you can think of all the things that we are using these days, like the portable consumer devices, like laptop, PCs, smartphones. And actually, it's very hard to imagine how could we use a smartphone if we don't have flash memory, right? Because I mean, imagine that you want to use a hard disk drive in your smartphone. I mean, it's not going to work for sure, because with all these movement that we have with our smartphones, for sure, HDD is going to broke, is going to fail. So, but the thing is that endurance for flash memory is limited. So for SLC NAND flash memory, we have this endurance around 10 to the power 5 or so. But by increasing the number of years, you can see that we have also reduction in endurance, that because of also using higher density circuits. For MLC NAND flash memory, you have less endurance. And the reason is that essentially what endurance affects, that program arrays affect, is that you will basically, the margin between your state, like the threshold voltage, they are getting closer and closer, right? With SLC flash chip, you have more space, more gap between two margins. So in the end, you can tolerate a higher number of program arrays. But when you use MLC, you have less margins, and basically you will have less endurance. And for TLC, actually, just a few, less than 1,000, at least for the measurement that we had in 2015 or so. So the thing is that P cycles provided from NAND flash memory is around few thousands. But P cycles, which is required by the standard, is that, so this is a written standard in STEC, which is writing, so we should be able to write the full capacity of the drive 10 times per day for 5 years. So that's a measurement for the lifetime, right? So if you want to do it, you need actually P cycles more than 50K, which, SLC can somehow provide it, but with MLC and TLC and QLC, we have a lot of challenge. So you can see that actually, even though, flash memory was kind of emerging technology like 2 decades before, but because of all the research that many people have done and work on that to basically make it happen, like the improvements in the architecture and the organization of flash memory, the circuit, and also the architectural work that eventually happened. I mean, make these SSDs possible, because SSDs are kind of, they are essentially you're designing a system when you design it, when you build SSD, because you have flash memories, but that SSD is gonna basically manage a lot of details that you have in flash memory, in order to make sure that you don't actually, basically your device does not expose errors as much as possible to the system, and also many other unique characteristics of flash memory. So because of, I mean, all these researches that have been done, and also the push from the applications, you know, because of people know that for smartphones, for portable devices, we need dense and reliable memory. So basically nowadays we think that flash memory is this kind of, you know, stable technology that we are using every day. So I like to mention it because that depends the way that we are thinking and when we are focusing. I mean, there are many emerging technologies nowadays that people think that they are cannot basically have impact. But the thing is that if you see some motivation, or you see some basically reason that they can provide good performance, or good energy, or good area, or reliability, it makes sense to invest time and do research. And basically, in the end, we can make the life easier for all of us. So basically, the lifetime of endurance, I mean, the endurance of flash by scaling, you can see that is actually reducing by, I mean, kind of exponentially. And at the same time, you need to add more error correction code to tolerate these errors. So your flash chips are gonna basically will get more expensive and more costly when you want, for example, to have this 3-bit MLC, which is TLC actually. So MLC is multi-level cell, but in the thing is that mostly in papers, when they say MLC, they mean 2-bit per cell. So for 3-bit per cell, we use TLC, which is triple level cell. And for 4 years, we use QLC. But yeah, so basically, you need to add more ECC. And at some point, you need to question. We want to, basically, we are using TLC, QLC to improve density and provide better, basically higher capacity. But in order to make it happen, we need to add more ECC. And that can cause essentially also capacity overhead. I mean, it has also other overhead, like the performance, like the power, I mean, all these things, but it also has capacity overhead. So we need to be really intelligent in how we are managing these errors. And from your understanding in the DRAM part of this course, you know that basically ECCs are good for fixing or correcting errors that we don't know the reason of them, right? They are quite random. But as soon as we understand the reason behind some errors, we can actually design intelligent architectures and techniques in order to fix those errors. So for example, I mean, all the works that we have done also for DRAM, right? So like the RowHammer, you know, so you can, there were some people that say that you can easily use ECC and fix that error. But the thing is that when the problem is getting worse and worse, that ECC is going to be huge overhead. And we need to understand the problem well to design intelligent, basically, solution. And here is also the case. We see how, by understanding the source of these errors, we could actually design intelligent techniques in order to fix the errors. So I like this analogy. Basically, you can consider your flash memory as a noisy channel. So essentially you write to your channel and then you read your channel. But in between in your channel, you will have a lot of noises. So basically what we had in the past is that, so we have these noisy, or let's say error-prone flash chips, and we have a lot of, I mean, high raw bit error rate. So, and then we need, in order to reach to uncorrectable bit error rate less than 10 to the power minus 15, which is again is coming from standard. So you need to make sure that uncorrectable bit error rate is less than this number in order to, such that you can use your device. Otherwise, your device is not usable. So you need to use a very complicated and costly error correction, right? So this is what we had in the past. But we think that with some memory signal processing techniques, we can have lower bit error rate. And then essentially you can have more efficient error correction code and also less costly ECC. So basically our goal is to build reliable error models for NAND flash memory and design efficient reliability mechanisms based on the model. So this is the technology that you have actually error everywhere in flash memory. So basically, when you want to write, you first need to erase your block. I mean, erasing happening in block granularity, I forgot to mention. So as I showed in the first few slides, we have these blocks and pages, right? So when you want to erase your flash memory, you need to do it in block granularity, because in order to reduce the overhead of erasing and actually increasing the bandwidth of erasing, because erasing is actually quite time consuming. But programming and reading is happening in page granularity. So first, in order to write, you need to erase your block, and then you can program your page. But the thing is that when you erase your block, you cannot, basically your erasing procedure is not perfect. So there are, so the function of erasing is actually to move all the electrons in the charge trap, or let's say the floating gate, to the substrate, right? So you want to make sure that your the threshold voltage of that transistor is back to the nominal threshold voltage, right? But that erasing procedure is not perfect. And as a result of that, there could be some electrons that still they are there. So your threshold voltage is decreasing, but it could happen that you don't have that nominal, the lowest threshold voltage that you were expecting. So basically, we may have some issues in errors in erasing block. We have some errors in when we want to program. And then when you want to, also when you do programming, you may have some neighbor page program and read kind of cell-to-cell interference, which you can see some analogy between this and RowHammer and RowPress, probably. So, I mean, the mechanism and error technique is different here, but yeah, I mean, making analogy is making the content easier for us to understand it. And when you, and essentially you also have this retention error that if you write to your flash memory and don't read it for, let's say, 3 years, basically good luck. You may not be able to actually recover your data. I mean, usually it doesn't happen with nowadays SSDs, because they have a lot of internal management tasks that they are actually refreshing and making it happen. But with all those cool disk, like the USB drive, right, that we were using, I mean, still we are using. So with them, actually, I wouldn't store my data and don't touch it for 3 years or 5 years, because there is no technique there to fix those errors. Okay. So yeah, as I said, I mean, goal is to understand the errors and develop efficient techniques. And our approach is to have solid experimental analysis of errors in real MLC NAND flash memory. So this paper, which I mentioned that we will also assign it as a paper review, is actually make a nice summary of different works that people have done in the understanding of types of error. So we need to understand the error, the sources of error, such that we can intelligently fix the error. And different techniques that people develop to basically resolve these errors. So we're not gonna see all these techniques in detail in today's lecture, but we're gonna cover some of them. So let's have a quick look at experimental characterization methodology that we have done. I mean, similar to RowHammer study that, I mean, all DRAM study that we have done with SoftMC and later on with DRAM Bender. We have this also infrastructure that we have used for studying flash memories. So this is a FPGA board, and here you can see a Vertex Xilinx Vertex FPGA that essentially we implemented NAND flash controller inside this FPGA, and we had some NAND flash chips that basically this controller were managing NAND flashes, and basically we managed to instrument NAND flash chips closely and understand many details of them. So if you're interested, you can also see more information about infrastructure about this paper. And also we, as I said, I mean, we use this infrastructure in many papers. So basically, we will focus on 4 types of errors mostly. So one of them, one category is those that caused by common flash operations, like the read errors, error errors, and program and interference errors. And there are some errors that they caused by flash cell losing charge over time, which is retention errors. And as I said, this retention error is especially problematic in MLC, TLC, and QLC flash memories because your margins are closer to each other. So basically, the methodology is that when we erase a block, we have some erase errors. So we want to measure those errors and understand them. So when we program, we have also our program process is not, let's say, completely ideal. So we have some program errors. And we have also retention errors. And when we read pages, we have read errors. So basically, we want to completely understand all these. So we characterize errors and error rates into, I mean, common technology NAND flash memory by that time, 3x and 2y nanometer. And basically, we quantify raw bit error rate. Raw bit error rate is the error rate that is before ECC. So you have some raw bit error rate, and depending on the strength of your ECC, you should be able to fix some of these errors. And then in the end, hopefully, you will reach to that uncorrected bit error rate less than 10 to the power minus 15. But in order to achieve that, you need to make sure that your raw bit error rate, which is the input to the ECC, is less than something. Otherwise, you cannot do it. So we're gonna focus mostly on the characterization and this quantified raw bit error rate. So let me check. Let me cover the first characterization result, and then we can have a short break and then continue with the rest. So the main characterization result is that basically we have erase errors. So as I said, for that we count the number of cells that fail to be erased to 1-1 state, which is the erase state, right? So basically we do erasing, and then we read from that block and check that if all the pages in that block, it has 1-1, right? So there could be some cells or pages that they have non-1-1 state, which shows that our erase procedure was not perfect. And we also, we want to check program interference errors. So we compare the data immediately after page programming and the data after the whole block being programmed. So essentially when you program, you will have some interference to neighboring cells. So we want to measure that as well. And we also want to measure read errors. So we continuously read a given block and compare the data between consecutive read sequences, right? And during the time, you can see the basically read errors. And for retention errors, basically we compare the data read after an amount of time to data written. And basically we characterize short-term retention errors. And also we want to also characterize long-term retention errors, like the 3 years, 5 years. But the thing is that we are not going to wait for 3 years in order to do this experiment. So there are some models that basically with temperature, with increasing the temperature of your device, you can actually model the effect of retention error. So basically, when you bake in the oven by temperature like 120 25 Celsius, you can basically, with some other stuff, you can model the retention time of 3 years, 2 years, 4 years, something like that. So if you're interested, you can see all the details of them also in the paper. So these are the results. So basically, raw bit error rate increases exponentially with PE cycles, which actually, this is something that we can also expect, right? When you increase PE cycles, you will, the accumulation of all the, in non-ideal process, like the erase process, program process, read process. So all these errors will accumulate more and more, right? So when you have higher PE cycles, essentially you will have also higher error rate. And that's the reason that your endurance is limited by the number of PE cycles, right? Because at some point your error is quite high, which you cannot fix it anymore with ECC and other techniques. And then you will see that, okay, my device is dead and I cannot use it. So, and retention errors are dominant. You can see that, for example, for 1 year retention time, which is the green curve bar, the green line, you can see that basically more than 99% of all the errors that happened for this PE cycle was due to basically retention errors. So basically, if you really want to improve the reliability of your flash chips, you really need to work on retention errors. So that's one of the key observation here. And basically, retention errors increase with retention time requirements. So if you, this is also expected. If you need your data to be there for 3 years, you will have higher number of errors. If you want to have your data for 5 years without touching it or modifying it, you will have higher errors. So that's one of the important things. And I should also say that the raw bit error rate, which can be more or less fixed or corrected by ECC, is around 10 to the power minus 3. So when your raw error rate is higher than 10 to the power minus 3, then essentially ECC cannot fix it. Assuming that you don't have more intelligent architecture in your system, and your device is gonna dead. So now we want to discuss a bit about retention error mechanism. So as I said, what will happen when we have retention error is that basically your margins, your state will shift it, right? So here we are showing it very nicely that they are just shifted to the right, to the left, but they actually are also widening. But yeah, for simplicity, we can consider that they only shifted. So, and basically you will have different threshold voltage, and you need to basically adjust your reference voltages in order to still read from device correctly. And another interesting observation was that basically, from this figure also you can see those cells that they have higher threshold voltage, they are actually shifted more. So basically, changing from this state 0, 0 to 0, 1, they have higher probability. And also 0, 1 to 1, 0, they also have higher probabilities. And because of that, you can see this figure. So most of the retention errors that we observe is that they were from 0, 0 state to 0, 1 and 0, 1 to 1, 0. So if you are interested, I would suggest that you check this date paper in 2012, which actually basically in this paper, we analyze and characterize the flash chip to understand the source of errors. And later on, we use the understanding from this paper and also future study that we have done by that time to design more intelligent techniques. So Now I want to go to retention error management. But before that, let's have a very short break. The first break I'd like to be short because we started lecture a bit late. So let's get back to lecture at 2:15. 5-minute break. Okay, let's get started. We're gonna have a longer break, hopefully, in 1 hour. So yeah, now that we understand the part of these errors, understanding, let's go into retention-aware error management. So basically, the solution to retention error is quite simple. I mean, one solution can be basically we need to refresh periodically. So you need to basically change the period based on the PE cycles wear out. When you have a higher number of PE cycles, you need more frequent, let's say, refreshing. But when you have a lower number of PE cycles, you can have refreshing less frequent. So in order to implement this technique, we use a combination of in-place and remapping-based refresh. We're going to see later what does it mean exactly, but shortly, in-place refresh means that, as I said, you cannot you cannot control the reduction of threshold voltage, right, in flash cells, but you can always increase the threshold voltage, right? So you can actually periodically read your flash page, and if you're observing some errors or some potential retention errors, you can basically do some in-place refresh, right, by increasing the threshold voltage. But another solution, it could be also remapping. So you completely read your page and you bring it to the controller and then you write it somewhere else, right? You remap your data. And we're gonna see a lot about this remapping and this basically out of place update in SSD later, I mean, next week, which is probably you already heard about garbage collection in SSDs. Does any of you have heard about garbage collection? Maybe in Java programming? Yeah, basically, yeah, in SSDs also we have the process of garbage collection, which is very costly, and we will see later next week, hopefully. Okay, so yeah, if you are interested, this is the paper that you can also check for more detail. But here I will provide very brief overview of this. So basically, the key observation is that retention errors are the dominant source of errors in flash memory, and that limits flash time as they increase over time. So retention errors can be corrected by refreshing each flash page periodically. And key idea is to periodically read each flash page, correct its errors with using relatively weak ECC. So when you have this kind of error correction, I mean, the intelligent mechanism, one of the advantages of that, you can actually simplify your ECC, which can provide a lot of benefits. So you can correct its errors using weak ECC and then either remap it to a new physical page or reprogram it in place. So before the page accumulates more errors than ECC correctable threshold. And we can also have some optimizations by adapting the refresh rate to endured PE cycles. So, I mean, depending on the number of PE cycles, you can actually adapt your the refresh frequency. So there are two key questions here: how to refresh. One is to remap, as I said, I mean, to read it and write it somewhere else, or reprogram a page. In place update, as I said, we will see in the next lecture that actually in place updates are very, very costly in flash memories, and because of that, people are using out of place update. But here, because of its characteristic that you just need to increase your threshold voltage and you don't need to reduce it when you want to fix the error, you can actually implement this reprogramming in place update easier. And the hybrid approach of remapping and reprogram based on the cost function and trade-off analysis, we can do both, right? Whenever it makes sense, use remapping and sometimes reprogramming. And this is essentially actually what this paper proposed. And when to refresh, we can have fixed period. For example, let's say every week or every 2 weeks or every month or every day. Or we can have adaptive this period by considering these PE cycles, basically, which you can, when you have higher number of PE cycles, as I said, you need to refresh your device more frequently. And this is, again, what this paper proposes. So this is the in-place programming of flash cells. As I said, I'm going to cover it very, very quickly. So when you have retention errors, basically your margins distribution will be shifted to the left. And when you want to fix it, you need to just push it to the right, right? And since you just need to increase the threshold voltage, you can actually do it. And so the pro of this is that you don't have this remapping overhead. So no additional, I mean, you will see that for remapping, we need erase operations. You also have data movement because you need to probably move your data to the controller and write it somewhere else. So there are some issues with remapping, but there are also issues with in-place programming. And the one thing is that when you program your pages, actually, you will induce some errors to your neighboring cells. We're going to see more about. This is quite uncomfortable. You will see more in later this lecture that we have this cell-to-cell interference. So when you actually do in-place update or in-place reprogramming on your flash cells or your pages, you may induce some errors to your neighboring pages, so which gonna be problematic. But here are the results. So basically, with this ECC, if you only use ECC, like the basic technique, and this is so the code for ECC is BCH, which is I don't actually remember the name of. So this BCH stands for the first letter of three people, but I don't remember the name. Yeah, my bad. But yeah, basically, this is one of the famous error correction code that people use. So by increasing the ECC strengths, you actually can fix some of the errors, but not, it's very little, right? But by using this technique like the remapping-based FCR, hybrid FCR, and adaptive FCR, and adaptive FCR essentially has all the optimization, right? It's using adaptively adjust the refresh period, and also has this both in-place update and remapping. So we'll see that basically we can have significantly increase the lifetime of your device, which is quite significant. Again, this is a great example that shows the strengths of using intelligent techniques. I mean, once you understand the reason of that error, you can understand it and you can fix it by using architectural techniques or some other techniques. But just blindly try to fix the errors by ECC, in the end, is not going to provide anything. So, and this is the overhead analysis, like basically the refresh and hybrid refresh. So this is energy overhead. And you can see that if we do this refreshing less than one every day, less frequently than that, you will your energy overhead is less than 1.8%. And most of the time, actually doing refreshing once a week is enough based on our analysis. So, and you can see that actually the relative overhead is quite low when you do this refresh. So if you're interested, I would suggest that you check this paper. We will also assign this paper as one of potential readings that you can do. Okay, so now I want to go to the next topic, like the next error that we want to cover here, which is a threshold voltage and program interference analysis. So we have some key questions. The first one is that how does threshold voltage distribution of different program states change over flash lifetime? So we want to really understand how this, we know that basically when you over time with P cycles and also after some time, these are gonna move, right? gonna go to left or right, they are widening. So we have some understanding, but we really understand and model it the way that it changes, such that we can actually predict the threshold voltage. And when you predict the threshold voltage, you can actually predict your reference voltage that you need to read that device. So what currently devices are doing is, so you access your flash chip with a reference voltage, and you read your page, and then you try to, basically, for sure you will have some errors. I mean, it's kind of very unlikely that you don't see any error when you read from flash. They are known that they are very error prone. So then you try to fix the errors by ECC. If ECC succeeds, then okay, we are good to go. But after, especially when your device is aged, most likely ECC is gonna fail. And basically what controller is doing, it retries the read process. It slightly adjusts the reference voltage and access the flash cell again. So try to basically read the flash with different reference voltage. So this can be very costly in terms of performance and also other issues, but performance is one of the main issues. And that's one of the reasons that you will see also in this lecture, that when your SSD is getting aged, its performance is also decreased a lot. It's one of the reasons that, I mean, you may actually realize that your smartphone is getting, I mean, slower and slower after like 3 years, like 2 years. I don't know if you keep your smartphone more than that, but I used to keep them for a while. So, I mean, after some time, you can see that they are quite slow, right? And that's one of the reasons, not all the reason. That's not the only reason. But yeah, one of the reasons is because of that read-write process, which is very costly. So if you can predict the reference voltage that you need, you can actually quickly access your flash chip with the reference voltage that probably is gonna provide the best result. So the question, I'm repeating the question because audience over Zoom may not, I mean, cannot hear it. So the question is about the reference voltage that we want to refine is higher than the previous one or lower than? Both can be possible. So if the source is only retention error, because by retention error, actually your reference voltage is, I mean, your threshold voltage, they are decreasing. So you need to actually reduce your reference voltage. But that's not the only source of errors. So there are some other errors that they can increase the threshold voltage. And in order to fix that, you need to actually increase your reference voltage. So basically, the idea is that we want to model and understand how VTH changes. And then by understanding that, we want to design and design a predictor to predict the value for threshold voltage. And then with that, you can significantly reduce read error rates, and also, which, I mean, thereby providing better performance. I don't know why it's not showing. Anyway, it was supposed to be a Gaussian distribution. So we'll see also again, but the thing is that, as I shown for the distribution of threshold voltages, we have this, you know, the kind of, we actually modeled that with Gaussian in the earliest stages of this work. So we use the Gaussian model to kind of predict how this I mean, Gaussian distribution with additive white noises. So with that, we managed to basically model the way that threshold voltage is changing. But essentially, later on, we will see also in this lecture that we realize that Gaussian model is not enough, and we have to use more accurate distribution. So, so with this Gaussian model, we could basically we provide 95% accuracy, which might be okay, but in reality, we need much higher accuracy because, you know, the number of you have many flash cells, and 5% inaccuracy is also a lot. You know, there are too many flash cells. So you actually need to push for 100% accuracy. It's very similar to, for example, like branch predictor in processor, like the accuracy of branch predictor. So even though the current branch, the success rate for branch predictor is quite high, but still there are many researchers that people are pushing hard to get it to 100%, which is not possible. But I mean, close to 100% is something that we need to push. So yeah, this is the paper. But yeah, I mean, later on, I like to show this one. So basically, the distribution is actually when we use more advanced flash technology, like 1x nanometer. We will see that basically the distribution is not actually perfectly Gaussian. So in this figure, you can see that those points are measurements, like for example, the triangle, the blue triangles, right? They're actually measurement, threshold voltage from the device, from the real experiment. And that dotted or lines are modeled, right? The Gaussian model, right? So when we have 2.5 PE cycles, you can see that, I mean, more or less Gaussian model is doing fine. It's not terrible, and it's predicting basically the distribution well. But for example, when you reach to 20 kp cycles, you know, there are some basically threshold voltage that they actually spread it out, all the whole distribution. So and you can see that basically Gaussian is not capturing it. So it's really important to move on and improve it and basically use better distribution technique. In this paper, we show that by using a student's T-based distribution, we managed to provide much better basically accuracy. So with Gaussian, the average is around 2.6%, basically the error rate. But with normal Laplace, we can have this 0.61%. But the thing is that Laplace is quite expensive in time. So we realize that student's T is one of the very good trade-off that can provide good prediction accuracy, and also is very good in terms of performance. So if you are interested, you can go into the paper and read it more carefully. But yeah, I mean, essentially that's the idea. So we want to model the threshold voltage using some distribution, and based on that, we want to predict the threshold voltage. The thing is that, and so that's our understanding on threshold voltage, but we have also these program interference errors. So when a cell is being programmed, voltage level of a neighboring cell changes. So it is kind of similar to RowHammer, right? So the reason is that when you want to program a cell, or when you want to actually read from a cell, you need to apply pass voltage to other pages, right? We have seen that basically you have a page that you want to read or write to it. So other pages in that block, you need to apply pass voltage. Pass voltage is quite high. And that can actually, I mean, still pass voltage is less than program voltage. I mean, you can, for example, consider program voltage like 10 volts or 20 volts, but pass voltage is around 5 volts. But that's a little volt, I mean 5 volt, is also something that can cause some errors. So that 5 volts pass voltage can also increase the threshold voltage of basically those cells that you didn't want to touch them, but basically you can cause some errors with that. So, and with that, actually, as I mentioned, shifting in the distribution is not only shifting to the right, which is as a result of retention error. But with this effect, which I said, I mean, the neighboring interference, your actually distribution can be shifted to the right. And as a result of that, your threshold voltage is increasing, and you need to basically understand it. So these are, I mean, we already covered the two-step programming. So this is, we have this victim cell, like the victim row in RowHammer, and there are basically several neighboring cells inside, intra that page, and also neighbor other pages, right? That they can actually essentially affect the threshold voltage of that cell. So there is actually a model from industry study and some other papers that basically the delta V for the victim row can be calculated using this number, is this equation. So what this equation is actually, saying that you need to calculate the delta V of your neighboring cells, and also you need to correlate that with the capacitors of them. And as an average of all these delta V of all these neighboring cells, you will have some delta V in your victim cell. But the thing is that this formula is actually not accurate enough. And actually, it requires knowledge of coupling capacitors. Like, we don't know what are these, capacitors in reality. So we like to have a model that provides a higher abstraction understanding of it, such that we can model it accurately without going having knowledge of capacitors values. So basically, our idea is to empirically characterize and model the effect of neighbor cell voltage changes on the voltage threshold of the victim cell. And then we want to basically use a linear regression model to fit to connect changes of neighbors threshold voltage of the neighboring cells and the victim cell. So in the end, this model is a simple, basically linear regression model. And so you can basically calculate all these voltages, like the delta V of neighbor and V of B for victim. The only thing that you need to learn is these alpha values. And you can actually learn them by your analysis, right? You can characterize your device, and you can tune eventually these parameters. So that's essentially what we did. And so these are some understanding. Basically, immediately above cell inference is dominant. You can also expect that, right? So this is the victim cell. And the immediate above cell has the highest interference on that. So immediately diagonal neighbor is the second dominant. And we have also, but essentially, also, the two above rows, they have also effect on that. So this is really actually quite important problem, because many neighboring cells, immediate your neighbor or other neighbors with one indirection, they can have provide issue for the victim cells. So then far neighbor cell interference also exists. And the victim cell's voltage threshold has negative effect on interference, which means that when the threshold voltage of the victim cell is high, like in the highest state, the effect of interference is lower on that. So yeah, that's one of also the part of our observation. So yeah, we actually use this model for interference, and then we learn these alpha values. So this is in this analysis, we want to show the accuracy of the model. So the red dots, they are actually basically measurement of the threshold voltage. So in this figure, we have this voltage threshold after interference and threshold voltage before interference, right? So what you really want here is actually this solid black line that you don't see any difference, right? So everything is going the same. So it remain constant. As much as you increase your, when you have higher threshold voltage before interference, you want to have exactly the same also after that, right? But what we are observing here in reality is different. And you can see these red dots that they are basically show that we have some changes, right? When we write to the flash, as a result of interference. But the good thing is that the model that we designed, this regression model, could actually predict kind of this behavior. And with that modeling, we could understand and design. Basically, we could predict what could be the threshold voltage. If you're interested more, I would encourage you that you check this paper. But now we want to go into another interesting source of error, which is reference voltage prediction. I mean, this is a mechanism, but we want to predict read reference in order to basically fix the errors and provide better performance. So now that we have the model, that we understand the changes in voltage threshold, I mean, even the voltage threshold going down, or I mean, going lower, I mean, your margin shifted to the left or shifted to the right. Now you have this model. So you can use that to understand your threshold voltage, right? So this is what we want, basically. So when we have this kind of distribution, we want to have the, I mean, this reference voltage, we want to have it use here, which can actually minimize your errors. So, but if you, for example, put your reference voltage somewhere here, in the end, you're gonna have higher error rate. So this is something that we'd like to avoid. So we claim that there exists an optimal read reference voltage, and we just want to find it, with using our model. So this was, the distribution, and you have some basically, shifting. So here we are shifting to the right. So threshold voltage are increasing. So you just need to adjust your reference voltage, right? So reference voltage was there in V prime, I mean, close to V prime 0, but now we want to have this V prime ref 3. I mean, you were using a V ref 3, but now you want to predict and use V prime ref 3. So yeah, basically we need to do this learning. We do every 1000 PE cycles. And with that learning, basically, so since you don't do this learning very, very frequently, I mean, not that frequent, it does not have a huge overhead on your performance and energy consumption. But that 1000 PE cycle, as shown in this paper, is enough, just enough to give you a good understanding of your device. And then basically we optimize, we adjust this reference voltage. So as a result of that, we can see that we can, if we consider that the acceptable bit error rate is 2 times 10 to the power minus 3, which is a bit 2 times higher than what I said, but it depends on how actually your ECC technique is strong, right? So you can actually draw a line there. Everything lower this line, solid line, is acceptable. So you can actually still use your device. So the thing is that if you don't have any read reference voltage prediction, you will have this red curve behavior. And the number of PE cycles that you can tolerate is 2.5 K, right? Sorry, 2.5 times 10 to the power 4. But by using this reference voltage prediction, you can actually buy some lifetime improvement by 30%. So you can tolerate higher number of endurance, right? You have basically essentially higher endurance number. So read reference voltage prediction reduces raw bit error by 64% and increases the PE cycle lifetime by 30%. If you are interested more, I mean, you can check the paper for more details about this work. There's also, later paper that we have written in this topic. So would be nice if you can also check it. But yeah, as I said, I mean, I would like to quickly repeat these things. I will flash them quickly because we already covered them. So we saw that it's not completely Gaussian, especially when we are using more modern flash chips and when we have higher number of PE cycles. So we as a result of that, we use a student's T distribution. And here you can see that student's T distribution provides relatively lower latency compared to Laplace technique, and also provide better, around the accuracy of this Laplace. So yeah, I'm quickly, I'm skipping these slides because we already covered them. I mean, you have the idea of that, but basically, you can see that by increasing PE cycles, we have this basically the difference in read reference voltages in this figure. You can see. So the actual is the curve with star dots, but with this student's T, you can see that we more or less managed to predict and understand the actual behavior. And because of that, we could actually have row bit error rate similar to what we can achieve by understanding the actual values. Okay. Now let's quickly go into another technique which is more intelligent. I mean, this provides more understanding of the device, which is neighbor-assisted error correction. It's quite actually amazing, this technique. I really like it. So the goal is we want to develop better error correction mechanisms for cases where SEC fails to correct a page. So our observation so far is that immediate neighbor cell has the most effect on the victim cell when programmed, right? We observe in that figure that 58% or so, something like that, was a dominant factor, right, the interference. So a single set of read reference voltage is used to determine the value of the victim cell. And the set of read inference voltages is determined based on the overall threshold voltage distribution of all cells in flash memory. So that's, we should pay attention to this overall term here, right? So you have this distribution figure, which shows the overall distribution of all flash cells in that page or block or the whole flash chip. But if you have a more detailed understanding of that, you can actually make it much better. So the thing is that the threshold distribution of cells with different value in immediate neighbor cells are different. So if you condition your basically your distribution by the value of the immediate neighbor, you can actually more accurately predict the threshold voltages. So the fact is that, I mean, our insight is that if we know the value of the immediate neighbor, we can find a more accurate set of read reference voltages based on the conditional threshold voltage distribution. So here is an example. So we have this aggressor word line, and we have this victim word line, right? So this is the victim word line before MSB page of aggressor word line or program. When you program, this is basically the distribution of your victim basically row, right? But this shows the overall distribution that happens for basically for the whole cells that you have in that row. But if you condition it, like I like to show the distribution of the cells that the neighboring value is 1, 1. So you will see something like that. This is the distribution, the threshold voltage threshold distribution of this cells in victim row, that the neighboring value was 1, 1. This is and that is. And again for 0, 0, 1, 0, and 0, 1. And you will see that actually, if you condition this, you can fix the overlap issue, right? Because when you look at it as the overall distribution, you have some overlap. And no matter, I mean, yes, you need to push for this nominal voltage in order to reduce the number of errors. but you will have error because there is overlap here, right? But when you condition this with the value of your neighboring cells, you can actually get rid of overlap because, I mean, these two do not have overlap. Yellow curve do not have also overlap, and so on and so forth. So that's the idea, basically. So when we know it, we could choose a different read reference voltage to more accurately read the victim cell. So when you want to, for example, read the cell that you know that the immediate neighboring cell was the value for that neighboring cell was 1, 1, you basically set the reference voltage to this red line, right? And I think it's pretty simple. After that, I'm just flashing these. So yeah, and with that, you can actually fix the errors much higher, with more, more strongly. And essentially, you will also improve the performance. So here are the results. If you use only basically bit error, so like the overall, like the understanding of overall, that you have the distribution and you want to find the optimum voltage for the overall. So with that, you have this 3 times 10 to the power minus 4 bit error rate for the analysis that we have done in this paper. But using that basically conditional reading, you can actually improve a bit error rate or reduce bit error rate by 1 order of magnitude, which is quite significant. So yeah, essentially, it's actually it's a kind of you have a flow of this technique. So the thing is that if ECC fails, you need to read the immediate neighbor page. So you read a page, which, I mean, you can consider that as a victim page. So you read a victim page, and when you want to apply ECC, after that, you realize that ECC fails, right? So in order to recover from that issue, you need to read the immediate neighbor page, and then you will reread the page using the read reference voltages corresponding to the voltage distribution, assuming a particular immediate neighbor value. So if the neighboring value was, for example, 1, 1, I will opt basically just the reference voltage and retry the read process. And basically, you don't really need to actually, yes. So you will retry, and then you replace the buffer values of the cells with the particular immediate neighbor cell value. And then you apply ECC again. If your ECC succeeds, then you're done. If no, you can actually go to the next step by checking, for example, the next value, which one, for example, 1, 0. And then those cells that they have 0, 1 and 0, 0. So you can actually serially do that, right? So this flowchart actually explains the technique. But essentially what you will achieve here is that without this technique, which we call it NAC, you will have this number of PE cycles before getting to the highest raw bit error rate that you can tolerate. But when you apply basically NAC that fix using the value of 1, 1, you can actually go from this line to this line, which give you some improvement. And then when you apply the next one, which is the NAC using 1, 1 and 0, 1, you can do better, and so on and so forth. So these are the results. That this only using 1, 1 gives you 22% better higher number of piece cycles. And then with this stage 2, you can achieve 33%, and then you can achieve 39%. And basically, the thing is that all these improvement comes at relatively no performance overhead. I don't want to say that performance loss is 0, but yeah, essentially it doesn't have much performance overhead. Okay. Yeah, here in this analysis, we also analyze the performance. And you can see that when basically performance loss is 0 within nominal lifetime and with reasonable ECC failure. So when your P cycle is low and your ECC failure is also probability is low, you don't have performance overhead. But as soon as you increase the number of PE cycles and you have higher probability for ECC failure, you will see some performance overhead. And at some point, your performance is gonna basically reduce a lot. Okay, any questions? Do we have any question on YouTube? Are you guys enjoying the topic? Kind of. Yeah, I mean, this topic is actually quite fascinating for me still. I remember I read the first paper that date 2012 paper that I mean, Professor Mutlu's research group, the Safari research group, they basically released on that the study of Flash. I was actually at the end of my bachelor study in Sharif University of Technology, and I was quite excited about emerging memory technology, like non-volatile memories, like flash memories and stuff. And I saw that paper and I read it, and actually I enjoyed it a lot. And I think that paper and this line of research is actually show how actually, as I said, I mean, understanding the source of errors can lead to much more intelligent solution. And all the solutions that we developed, I mean, the course of these years, I mean, some of them are, so when we start the study of this, we were kind of late compared to the industry understanding. I mean, industry knows on that time that these are the errors sources, and they had also some techniques to avoid that. But the thing is that that wasn't clear for the academia, for people that doing research in academia. And using that, so we started a bit late, I mean, compared to the industry understanding. But from our research, at some point, we actually, we arrived or reached to the point that we were doing research on par with industry. And many of the techniques that Professor Mutlu's group have been developed during these years in flash memory and SSD, they actually have been used in some devices. So that can show basically how academia can affect industry. So in many topics, we think that industry are quite advanced and we are behind of them. But when you actually start, because you may be more efficient too, or maybe you have more, let's say, open mindset to understand the issues and fix the problems. Or basically, you're not bounded by some constraints that industries are, like in academia, for example, we are not bounded by time to market or many other stuff that relate to the way that industry people, they have to care about that because they need to have profitable product, right? So yeah, I mean, that's quite important to me. And I learned actually a lot from this line of researches. So I think we can have 10 minutes breaks until 3:10. And then we can continue by redistrib error handling. I think we will cover until 3D NAND flash memory. This topic we will cover next week together with SSD related stuff. So yeah, please come back at 3:10. Okay, let's get it started. Before going through these other topics and techniques, I'd like to make two quick announcements. We will release Lab 4 today, hopefully. So, I mean, it's going to be very interesting lab because, I mean, you will work with prefetching the simulator and you design your prefetching algorithm and you can test it. And so the deadline for homework 3 was supposed to be tonight. But as I realized that there was some issues with one of the understanding of one of the questions, and and we couldn't resolve it in time, we will extend the deadline for homework 3 until Monday midnight, basically. So if you haven't submitted yet, I mean, you can actually update your submission if you want. So yeah, I'd like to mention these two announcements, and we will release homework 4 by Monday, hopefully. Any questions about logistics and? Yes. It actually the initial plan was to release it last week, but we will release it tonight. Yeah, but the deadline for lab is kind of, I mean, it's not straight, right? It's not hard deadline. And actually, so we mentioned that all the submissions that you provide by the deadline, we will provide feedback, right, for the lab. But I mean, usually we are also waiting like one more week or some more days and check. So you have also some more days. Any other questions? Okay, perfect. Then let's move on. The next topic is about read disturb error handling. It's very also, again, similar to read disturbance error in DRAM that you already learned a lot about it. That will RowHammer, row press. But let's see this phenomena in this topic in flash memory. So basically, all scaled memories are prone to read the disturb errors: DRAM, SRAM, hard disk, and NAND flash. But we want to focus more on NAND flash memory. I'm not going to talk about the NAND flash memory background again, but you already know that we have blocks, and each block we have several pages. Erases is happening in block granularity, and read and program is happening in page granularity. And when you want to read a page, you need to apply pass voltage to all the other basically pages. And then for that page that you want to read, you just apply the reference voltage. I will skip these relatively quickly because, I mean, we already covered. And this is a very, again, brief overview of flash chip. I can stop on any slide if you have questions, but I think we can skip them. We already covered. Okay, here. So let us see the problem of read disturb problem. So we call this problem as weak programming effect. When we want to program a page, we need to apply high voltage. That voltage is relatively high compared to VPass. I mean, like 10 volts, 12 volts, 20 volts, something like that. But VPass voltage, as I said, is around like 5 volts. I mean, in this example, for example, as an instance. But the thing is that that 5 volt is just a little that can also provide some weak programming effect. And that can increase the threshold voltage of your cells, the neighboring cells. So imagine that you want to read the page 3 in this block. So you apply VPass to page 1, 2, and 4. And if you do it like you hammer it, like you read this page 3 several times repeatedly, you will see some errors in neighboring pages. For example, here you can see that this poor flash cell, it was the threshold was initially 2.4, and after this read disturb error, it will increase to 2.6, for example. Then when you apply, when you want later on, when you want to read page 2, you will apply a read voltage, read reference voltage of 2.5 volts. So this cell, it was supposed to be on, right, with this 2.5 volt reference voltage, but but because of these changes, this flash cell is not going to be on and cannot drain the flow, and eventually you will read it as 0, which is wrong, right? So that's potentially provides some error. We call it as read disturb problem. So this is the work that we done in the conference DSN in 2015. The executive summary, I will go over it relatively quickly. So read disturb errors limit flash memory lifetime today. And the result and the reason for that is that we apply high pass-through voltage to multiple pages on a read, and that repeated application of basically VPass can alter stored values in unread pages. So we characterize read disturb on real NAND flash chips, and we observed that by slightly lowering pass voltage, we can greatly reduce the number of read disturb errors. And some flash cells are more prone to read disturb, which we will see there how we can use that later. So we have two techniques. Technique one is to mitigate read disturb errors online. So basically, we tune VPass dynamically. We find basically we lower VPass in order to reduce the effect of this weak programming. But at some point, you cannot also reduce VPass a lot, because that can also provide some error. So you need to be intelligent and basically dynamically adjust VPass to make it work. And with this, we observed that flash memory lifetime improves by 21% on average in our experiment. And for technique 2, we actually recover after failure to prevent data loss. So you had a flash chip or SSD, and at some point your drives told you that, okay, there are some uncorrectable errors, and basically, yeah, that's a failure. We cannot use it. So you can actually do more sophisticated process offline in order to recover your data at least. You may not use your device anymore, but at least those data that you have there in your SSD or your hard disk or any storage, you want them back, right? So people are using more sophisticated techniques for that. And here you can also use implement a recovery technique after failure using actually the key insight from this observation that some flash cells are more prone to read disturb. We will see later how we can implement that. And with that, we reduce raw bit error rate by up to 36%. Okay, so this is observation kind of motivational analysis that we have done. When we reduce the pass-through voltage from 100%, which is the nominal VPass, by only 6%, like to 94% VPass, we can actually significantly reduce the effect of, reduce the number of errors. So here is read disturb count. The number of reads that happen in your, like the hammering row or or aggressor row or something like that. But as a result of this hammering or read disturb count, you may have some errors in your basically adjacent, neighboring rows, right? So by reducing the VPass by 6%, we can actually increase basically, what's this figure showing that? Normalize tolerable. Yes, basically the number of read disturb count that you can tolerate can be increased to 1,300, which is a lot. So by only reducing 6% in VPass, you can achieve 1,300 higher tolerability. So this is the key observation that, as I said, slightly lowering VPass greatly reduces read disturb errors. And basically, the technique is quite simple. We just need to tune VPass. So we dynamically find and apply a lowered VPass. And so here you have a trade-off, right? When you reduce the VPass, you may have actually some errors since your VPass is not high enough, right? And because, so when you apply VPass, you want to make sure that all the cells in that page will act as a resistor. I mean, the flash cell will be on. But since you lower VPass, there could be some cells that they act as a switch off because your VPass is not high enough. So you will basically generate some errors because of that. But at the same time, you reduce the number of errors causing from the read disturb, right? Because you have less amount for VPass. So this is a very nice, interesting trade-off analysis that we have here and we should actually explore. So for example, initially VPass was 5 volt. If we reduce VPass, for example, to 4.9, you will see that it's okay, nothing will happen. But when we increase it, reduce it more to basically 4.7, you will see that that red flash cell is not going to act as a closed switch. And basically your current will not drain, and essentially you will read 0, which actually you should have read 1, because this the corresponding flash cell in page 2 has lower threshold voltage compared to your reference voltage, but now you read 0, which is wrong. So you can see that basically we should be careful about that. So the key observation here is that we can utilize the unused ECC capability here. So the ECC capability, which usually we have, is, as I said, 10 to the power minus 3. But this is actually quite over provisioning. So this is ECC correction capability, but the nominal raw bit error rate that we have in normal operational flash, like especially when your flash chip is still young enough, you don't have huge number of program erase cycles, and basically your flash is also not aged. So you basically your ECC correction capability is high enough, right? So you can actually use this unused ECC capability by fixing to fix the errors that can cause by reducing the VPass. So we reduce VPass, we actually generate some errors, but those errors are not bad for us because we can fix them by ECC, right? But that reducing VPass have a more long-term effect on basically, because it doesn't provide, reduces the issue of weak programming, and you will basically avoid errors that are bad, you cannot easily recover from them. So that's actually very nice, I would say, clever insight here. So basically, ECC provision for high retention age and unused ECC capability can be used to fix read errors. And we use unused ECC capability decreases over retention age. And then basically we can dynamically adjust VPass, right? So when your device is aged, then basically you cannot reduce your VPass a lot, because then you will gonna cause a lot of errors. But your ECC is not capable of fixing that. So we should be careful about the VPass, basically. So yeah, in today's system, we conservatively set VPass to a high voltage, which can accumulate more read disturb errors at the end of each refresh interval. But we don't have no read errors. But the idea here is that we dynamically adjust VPass to unused ECC capability. It minimizes read disturb errors, but basically it can provide some read error, but you can fix them by ECC. However, if read errors exceed ECC capability, basically we need to adjust VPass. So we can increase VPass just a little to make sure that we can read better, I mean, with less errors. So we perform this VPass tuning once for each block every day. And we estimate unused ECC capability using retention age. I mean, from the number of PE cycles of that block and the retention, you can actually estimate. I mean, Flash controller has that information. And basically, we aggressively reduce VPass until read errors exceed ECC capability. And then we gradually, again, increase VPass until read error becomes just less than ECC capability. So just kind of, the tuning technique that we are using here. So for evaluation, we use a 19 real workload IO traces, and we assume that we have 7-day refresh period, which is okay. I mean, as we discussed, the refreshing that we can have, if we have it once a week, the overhead is quite relatively low, I mean, less than 1% or so. So, and we use a similar methodology as before to determine acceptable VPass reduction. So the overhead for a 512 gigabyte flash drive, we observe that we need 128 kilobyte storage overhead for per block VPass setting. And we need like around 25 seconds per day for this VPass tuning, right? Which is also not a lot. I mean, especially when that 25 seconds per day is not a lot, but the more important thing here is that your flash chip or your SSD is gonna be idle also during the day, especially even in enterprise data centers. So there are many techniques actually nowadays that they're predicting idle times of SSDs such that they can basically issue internal management task of storage while it's idle, right? So having your SSD having idle is not something that is not so common. It's actually happening, and the only interesting question is how to predict idle time soon. How to predict accurately and in time, such that you can make a plan for that. We will see later, next week, when we are talking about garbage collection, how we can leverage this lifetime, basically. The idle time of SSD. Okay, so yeah, this is the result. So we can see that the average lifetime improvement is 21%, but this is actually a bit skewed because, so there are some benchmarks that for some reason we don't observe a lot of read disturb. The reason could be they don't have a lot of, like read hammering access, like the read access to one row or page. But there are some applications that you can see that VPass tuning significantly increase the number of PE cycles. The lifetime. So, the average is 21%, but for many, for some benchmarks, you can see that the improvement is quite significant. So, but this is the technique that we have proposed to fix the issue online. But once your devices fail, you have this failure, and you have more time and more resource to fix the issues. So we will develop an idea using this key insight. So there are some cells that they are disturb resistant, which means that as a result of read disturb, the threshold voltage is not going to change a lot. And there are some cells that they are disturb prone, so their threshold voltage will change a lot. So we will see something like this, when you have, for example, N read disturbs, there are some cells that they change a lot, and some cells that they don't change, they just change a little, like the disturb resistant. And if you have understanding of them, actually you should be able to fix some errors. So here we have, for example, 4 cells in ER state and 4 cells in P1, right? And you can see that, for example, these 2 cells, green one, are disturb resistant. Yeah, disturb resistant, and these 2 are prone disturb prone. So when you actually cause 250K read disturbs, we will reach to this position, right? That basically you have this overlapping and shifting of distribution, and you have some errors. But the thing is that those are that they were prone to disturb. They actually, move a lot. These 2P, they actually move a lot. And those that they were resistant to this read disturb, they didn't move a lot. So as a result of that, someone may think that actually those are that they are resistant, they are good for us, but actually it's not the case. I mean, both are not good, because so when you have this issue, you will actually what we usually do, we predict the optimal reference voltage and try to read your data, right? The thing is that this P, which was belonged to this state, now we're gonna read it as P1 state. But this cell, which was also belonged to P1, now that we have this shift widening stuff, we will read it as ER state. So this one is also problematic here for us. So, but the thing is that when you know it, you can actually try to fix it. So disturb-prone cells have higher threshold voltages, and disturb-resistant cells have lower threshold voltages. But as I said, this one will have problem because you will read it wrongly. So the key idea is using this. So we basically, the technique triggered by an uncorrectable flash error when your device basically fails. We back up all valid data in the faulty block. And then we disturb the faulty page 100K times or more than that. And then basically we compare the threshold voltage before and after we disturb. And then basically we do this to understand, basically select cells that they are susceptible to flash errors. So basically we want to understand that what are the resistant, disturb resistant and prone disturb cells. So yeah, we do this analysis and we predict them. And once you know it, then basically cells with more voltage threshold, cells with more voltage threshold shift are disturb prone. And basically we need to consider lower threshold, voltage threshold state. So yeah, we know that, for example, this P, even though we are seeing that it's in the P1 state, but the moment that we understand that this is it's going to be disturb prone, we just consider it in the erase state. And that can fix the error. And cells with less voltage threshold shift are disturb resistant, and we basically consider them in a higher threshold state. Is it clear? Okay. So this reduces total error count by up to 36% at 1 million read disturbs. And basically, ECC can be used to correct the remaining errors. So basically, we kind of manually fix some of the errors using this analysis, this observation. And then the rest of errors, ECC will hopefully fix that. And you can use your device if you still trust it. But the good thing is that still, I mean, at least you have your data back. Yeah, and this is the result for read raw bit error rate for this for with no recovery and RDR technique, which I mentioned. And as I said, this 36% improvement. So if you're interested, I would encourage you to check this DSN paper. I like to quickly go over retention error handling as well, because it also uses a very similar idea as we also discussed in the previous technique. So basically, data retention in flash memory, we should actually characterize them. I mean, to characterize retention loss in real NAND chip. And then after characterization, and when we understand it, we can optimize read performance for all data, and then we can recover from the issue. So this is actually some report that basically has been posted before. Basically, you can see that an unfortunate tale about Samsung's SSD 840 that read performance degradation. So basically, this is something that you also observing in your daily life, that after some time your devices are getting slower and slower. And the reason is not magic. I mean, there are many reasons. I mean, aging is something that happens in all devices, like the cores, memory, storage. But specifically in storage, by aging and that retention error, you need to do the process of read retry a lot. So you read your page from your flash memory, you check the ECC and ECC fails, and then essentially you need to retry the read. When your device is quite aged, you need to actually, at some point, you need to retry like 10 times or even more. And you will see that basically the read latency is gonna increase by 10 times. Because in the past you had only one read access, but now because of the ECC errors, you are accessing your reading data like 10 times or even more. And that's essentially one of the reasons that why SSD or flash chips are getting slower and slower. So, and basically reading old files is consistently slower because of the higher retention errors, right? And they basically observe like very slow throughput for them, like 30 megabytes per second. And for those files that they were kind of new, they actually observe 500 megabytes per second. So kind of, around 1 order of magnitude, or actually a bit more, reduction in basically in throughput because of retention error. So this is the analogy that one of Professor Mutlu's former PhD student, Yishin. Yishin and Yukai, both of them, they have done a lot of study. I mean, many of these studies that I'm also discussing today is actually Yishin and Yukai, they drove in there when they were PhD students of Professor Mutlu. And this is one that Yishin has been used, analogy. I really like this analogy. So why is all data slower? And the reason is retention loss. So retention loss, charge leakage over time. I mean, we already covered these. I don't want to go into detail again. So the side effect is not only about reliability or flash chip, I mean, your SSD. It's also about the performance of your system, right? So in order to fix those errors, you need basically you have some performance overheads. So fixing this kind of issue not only provide better reliability and basic robustness to your system, but also provide better performance. Okay, so yeah, we already covered these, and this is the experimental testing platform that I already showed. So this is the actually distribution that we observe from the real experiment. So these are the basically distribution of thresholds after different retention time, like the 0 day, 1 day to 40 day from that particular device that we tested. And you can see that after 40 days, we are basically the threshold voltage, they are actually shifted to the left. And also the graph is also widening. I mean, similar thing that we were expecting. So we know that threshold voltage reduces over time, and it's widening. And we have basically raw bit errors, and we need ECC. And at some point, raw bit errors are greater than ECC correctable errors, which normally by then your device is dead. But our goal is to actually find the reason of them and fix it such that you can still use your device and increase the lifetime. So we need to also increase read latency as a result of read retry. I already talked about read retry process, right? So we already covered that. Why is all data slower? So we have retention loss, which as a result, you have leak charge over time. You need to generate, so that generates retention errors. So essentially, controller need to do read retry, which in the end you will have longer read latency. So now how we can optimize it? So we want to optimize the performance for all data. Basically, our solution is to find the optimal read reference voltage, predict it soon, with minimal read latency, such that at least you can accelerate that read retry process, because you can read your flash with the reference voltage that probably your ECC capability is enough to fix error. So the good thing is that this OPT, which is the optimal read reference voltage, is changing gradually, and it's unidirectional. So it decreases over time because of this phenomena of retention error. So retention error is always, in one direction. So we can model and predict OPT. So we have two components here. We have this online pre-optimization algorithm that we learn and record OPT and performs in the background once every day. And then we have this simpler read retry technique that if recorded OPT is out of the date, we need to basically we read retry with lower voltage. So this online pre-optimization algorithm, we trigger it per day, as I said, and we find and record an OPT as per block. And this happening background such that you don't see the performance overhead of that. Okay. So, and once you have this optimum voltage, you can actually improve your read retry process, and you can improve the performance a lot. Okay, so these are some results. So using this technique, which we call it ROR, we can reduce the read retry count, the number of read retry counts, like by 70%, which is a lot. And then the VCH decoding, the ECC decoding latency has been also reduced. And in the end, as a result of that read retry count and lower latency in VCH, overall we have lower total read latency. So, this is not very important for new files. Those files that are new, probably they don't have that retention error a lot, and this technique is not for them. But for those data or files that they are basically have lots, long retention time, which we call them old, you're gonna have a lot read retry, and the performance for them is quite low. So by this technique, actually, you can at least provide some better performance. Okay. But there are at some point cases that you cannot fix the issue by this optimal voltage. So you predict and use that optimal voltage, but even with that optimal voltage, sometimes your errors are, the number of errors is quite high. Bigger than the strength of your ECC. And then your device is dead. So you need to recover from that case, right? So we have some old data that we want to fix them and recover them. We're gonna have the same, relatively very similar idea as we have also before in the technique that we talked about, read disturb. There are some basically cells that they are low leaking cells that basically they leak, less. And there are basically cells that they are fast leaking cells, and they basically after end day retention, their their threshold is quite low. It's decreasing a lot. So again, similar idea. You have this slow retention, fast retention, and in different situations. And after that, you have this analysis that fast leaking cells have lower VTH, and the slow leaking cells have higher VTH. And once you know it and you understand from your characterization that what are the slow and fast cells, you can actually fix the issue. You can slightly change them and then see if ECC now is able to fix error or not. That's the technique that we have proposed for retention failure recovery. So yeah, we expect to eliminate 50% of raw bit errors using this technique, and then the rest of errors, hopefully ECC can correct, and then your device can be recovered completely. So as a conclusion for this technique, we have retention loss, which provides longer read latency. I mean, as well as other issues like, as I said, robustness of your system, reliability. But yeah, so we propose a retention optimized reading, ROR, which learns OPT, which is the optimum voltage, reference voltage predictly. And with that, we can have 71% shorter read latency. And we have this retention failure recovery technique that use leakage property to guess correct state. And we could fix 50% error. We can basically reduce the number of errors by 50%. And the rest of errors, ECC can fix them, hopefully. If you are interested, you can check this paper in HPCA 2015. Okay. We are on time still. So this is the last topic that I'm gonna cover today. As I said, 3D NAND flash memory. I will cover it next week. Let's quickly go into it, but before that, I like to stop if there is a question. Yeah. So the question is, yeah. So the question is about for fast and slow leaking, where do we store basically the characterization, right? So no, actually we don't need to store them in SSD. You can actually decide it. You can store it somewhere else. So we are doing this process when your device is dead, right? When your device is not recoverable, and we want to recover it. So your SSD is not. So then we don't have that kind of storage overhead that. So we are storing the characterization of these cells while SSD is working, right? So basically, we trigger this technique when the device is dead, and then in order to understand that what are the fast leaking and slow leaking, you can basically you can do it online. When you want to do this technique, so you basically write to your flash, to your block, and then basically profile the retention errors. Like for example, you accelerate the retention time by baking in the oven, and check the number of errors, and basically check the threshold voltage of every single cell, right? And from that profiling, you can realize that what are the fast leaking and slow leaking. So the result of this profiling, you can store it basically wherever you want. It's not. But the thing is that we will do it to recover the SSD files. And then once you recover it, your SSD is back again, and you can use it. And you don't need actually that information anymore, because that information might not be usable also for the next recovery. Because as you also, I guess you also learned in DRAM, right? We do this profiling of refresh, like the retention. It's not something that you can do it only once and then you can use it. After some time, the result is changed, has been changed, and you need to do it again and again, right? Yes. Any other questions? But that was a very good question. Thank you. Okay. So until now, all the techniques that I discussed and characterization, they were doing like using that infrastructure, and we were instrumenting the real NAND flash chip. So basically, we were sitting on the flash controller that we have observation of flash chips, and we could actually do everything we want. We can basically optimize, adjust threshold voltage, read the calculated basically VPass, and all these things that I already covered. But in this, the second, the last work that I'm going to cover today, is that we did analysis on larger scale feed analysis. So this is the analysis that we have done with Facebook. This was a collaboration with them. So in this analysis, we actually we analyzed SSD errors on Facebook systems. And essentially what we care here is actually at the software level, right? So there could be some, there are some errors in flash chips that they are correcting by SSD internal mechanism that it's not completely actually disclosed. So, but here from this analysis, we have some SSD errors that we can observe from the operating system, right? So this analysis has been done from the software layer, not from the, device level. This is important because it affects some of the, we should take it into account when we are observing the results. So the first key observation that we had is that, so we tested many SSDs. I don't know actually how many. But the interesting thing is that there are some SSDs, a few SSDs cause most errors. So not all SSDs are basically error prone, right? We have also similar observation in DRAMs. Like there are some DRAM modules that they are more error prone. Ismail can correct me if I'm wrong. But yeah, some DRAM modules are basically more reliable. But yeah, the same thing is happening for SSDs. There are some SSDs that they are more causing more errors, and basically, yeah, some of them cause the most of the errors. So this is the summary of the analysis. So we have this new reliability trends. So we analyze SSD life cycle. We consider read disturbance, temperature effect, and access pattern dependence. I'm not, again, going to cover this work in detail. I will just flash some key observations here. But if you're interested, I would suggest to check the paper. Last semester in a seminar in computer architecture, if I'm not mistaken, or maybe last year, we also discussed this paper. So if you're also interested, you can check that talk in seminar in computer architecture course. We had actually quite a good discussion about this work. So for the SSD lifecycle, we actually realized that early detection lifecycle period distinct from hard disk drive lifecycle. Are you aware of this bathtub curve? Have you ever seen in some other domain? You've seen it, right? So this is a kind of life cycle that we are observing in many, many domains. It's not only in electronic devices. There are also some similar analysis have been done, for example, for cars, But essentially what we are seeing here is that we have this early failure period, that there are some devices that you haven't tested them enough. And basically, as a result of that, you see they will fail a lot in the beginning. And once your device survive the early failure period, probably is going to survive for a long time. So we have this useful life period that basically you can use your system. But at some point, your device is going to age, and you're going to be in wear out period that you will see the result. So the question that we had is that, do SSDs display similar life cycle periods? We use the data, basically, written to flash to examine SSD life cycle. So we use this time-independent utilization metric. I mean, I'm not gonna cover it, explain in detail because it needs some more background information about the paper, but you can check the paper. So this is the result that we observed. We somehow observe this bathtub curve. So we have this early failure period, and then we have kind of useful life period, and then wear out period. That we observe a lot of SSD failure rate. But at the same time, we also observe this early detection period that bit error rate was quite low, which is against of the bathtub curve. But I mean, we don't know exactly also the reason about that. So another topic that we were interested in, this topic was the effect of temperature. So basically, in modern SSDs, we have this temperature sensor that you can actually read the temperature, working temperature of your SSD, and you can correlate errors with temperature. I mean, if there is a correlation. So this is the result that we observed for many cases. When you increase the temperature, you likely have higher errors. So temperature is actually one of the important parameter here. So when your device is highly load and it's working hard, so the temperature is getting higher and higher, and as a result of that, failure rate is also increasing. So, but there are some technique in order to avoid that is to throttle accesses. I mean, SSD can throttle accesses, reduce the bandwidth just to lower the temperature, or SSD can completely shut down, you know, and that can also reduce. I mean, that has some performance overhead, probably, and not probably. I mean, for sure. But yeah, I mean, it will reduce temperature and might be. It might make sense when you have because of if such that you can reduce number of errors. I mean, as a trade-off analysis. But yeah, basically, there were actually some SSDs in the field that they were doing such throttling techniques, probably, that basically by increasing the temperature, the bit error rate does not correlate well. So yeah, so basically we hypothesis that some SSDs in the field they are actually using. People were curious about those SSDs vendors, but but you know, in the papers we don't publicly mention the SSD names or DRAM. We usually say SSD A, SSD B, C, D. You know, but yeah, if you're really interested to know about which SSDs, I mean, during that time you can. I mean, not only in our paper, in also other papers. One solution is to directly, privately contact the authors, and they may share with you privately because they can do it if they want. But publicly, it's not something, it's a good thing to do. Because actually the goal of these researchers also is not to compare vendors, you know. I mean, there are many important, let's say, widely used, vendors that they are all common, popular. And we just want to show that how the character error is happening with them. So throttling SSD usage helps mitigate temperature-induced errors. So for read disturbance, we do not observe the effect of read disturbance errors in the field. So even though we actually observe a lot of read disturbance error when we were testing flash chips directly, but because of many reasons, we like some reasons that SSD internally actually fix those errors. So they have we have this complicated ECC that modern SSDs are using, and at the same time, flash controller in modern SSDs are also very intelligent. I would say that flash controller is a lot more intelligent than DRAM controller, because DRAM controller is not doing all these intelligent mechanisms that we were discussing. And that was also part of your the beginning of this course, that we were showing that by making DRAM controller more intelligent, how we can actually fix many scalability issues of DRAM. But flash controllers are quite advanced, and they are actually implementing many mechanisms here to fix the errors. Yeah. We also quantify the effect of page cache and write amplification in the field. I'm not going to explain them because you will understand about page cache and write amplification and hopefully next week. But yeah, we don't need to cover it today. So yeah, but basically we also consider the effect of them in this analysis. So there has been other works are also NAND flash memory modeling and issues. This work in HPC 2017 is actually quite exciting, and I really encourage everyone to check it. This is also another one, and we reached to our 3D NAND flash memory reliability. So next week we will start with 3D NAND flash memory reliability, and I think I need like around 30 minutes to cover this part. And after that, we will go to SSD internal organization. What's the architecture of SSD? What are the internal, I mean, not all internal management tasks, but some SSD management tasks. And hopefully we see some architectural also innovations there that provide huge performance improvement. Any burning questions? Then have a nice weekend. See you next week.